Hello everyone, welcome to the last lecture of the course. In this lecture, we're going through problem solving related to chapter 3, which we talked about chemistry of metals in environmental system, and also chapter 4, in which we covered redox chemistry. So we're going to solve 4 related questions. The first one is mainly the conceptual problem, similar to the one we had in the homework, and the last 3 is basically more on the numerical side. So let's focus on the first problem. It's basically a reaction diagram. We saw in the lecture, especially in chapter 3, that this reaction diagram would help us a lot to figure out about the possible reactions that are centered around metal. And it would just help us to organize our thoughts before driving the equilibrium expressions. So it was a good practice to always look at reaction diagram and build reaction diagrams before we actually solve it. So this is a specific question. It's similar to homework 4. It's asking us about like copper ion. So basically copper ion would be the center, copper 2+. Then it would give us the information about the redox reaction. It's 2 redox reaction. So basically we have 2 redox reaction for copper 2+. So the first one, it's forming copper plus, and the other one is forming copper 0, which is in the solid phase. So far we decoded up to here. So 2 redox reactions. Then it's giving us information about the complexation basically. So copper 2+ form complex with up to 2 hydroxide. So that would be copper 2+ with hydroxide up to 2. That means copper with 1 hydroxide. The charge would be plus, and this would be beta 1 for copper 2+. And we know it's basically beta 1 copper 2+ of hydroxide. And also the second one, copper OH2, still in the aqueous phase, so this would be beta 2 of copper 2+ with hydroxide. Then so we decoded also this line. So we also have the formation of 2 precipitates. Oh wait, so we also have, we need to address this part also. So we took care of the hydroxide with copper 2+. And also copper 2+ can form complex with 1 chloride. So basically with Cl-. So as the ligand, this would form only 1 complex. This would be beta 1 of copper 2+ with Cl. Then we also have the complexation of copper plus form a complex with 1 chloride ion, and that's it. So copper 1+, which was the product of one of the redox reaction, can also complex with Cl, and then the charge would be basically 0. They cancel out. This would be beta 1 of copper plus with Cl. So that's all about the complexation, but the question is talking about also the precipitation. So it seems we have 2 possible precipitates. And when we look at the charge, we see that there's like a 0 charge here, as we expect for a precipitate. So it means it was copper 2+, and here also copper 2+. So the charge was canceled by 2 hydroxide or 1 carbonate. That's why it's copper 2+ and not any other forms of copper. So basically this would have hydroxide precipitate. So this would be copper OH2 solid with KSP of hydroxide, and also with CO3 2-, which would form copper CO3 solid, and then this would be KSP of CO3. So we decoded also the precipitation. So the only thing that is left, so it's just the acid base. So it seems it's an open system. So basically CO3 is in equilibrium, as always, with bicarbonate. The expression that describes this is Ka2, and then this is in equilibrium with H2CO3, Ka1, and now this is in equilibrium with air, open system, with CO2 gas, and this would be HPM. So, and that's it. No more information that is given. So this is basically the whole reaction diagram for this given system. So we just need to label the type of the reaction that we are dealing with. So this part is all about complexation. So they all aqueous species. This is all about redox. This is all about precipitation. This part is about acid base. And this is about gas-liquid equilibrium. So yeah, so we basically included all types of reaction that are involved. So later on, if we're looking for species that are in the aqueous phase or dissolved species, this would be all of these complexes with this redox species and also this acid base species. So these are the two that cause lowering the total concentration of copper through precipitation. So, but this reaction diagram, even when it's not asked to do it, it's a very good practice, and also it's a very good guideline to guide your following equilibrium expression reaction. So this would be very beneficial, and it's highly recommended to use it for also other more numerical problems. So let's go to question number 2. So basically in this question, we're talking about iron, specifically iron 3+, so Fe3+, and then it seems it's involved in a redox reaction, complexation, and some sort of precipitation. And the reactions are all given. So the question is not asking us to construct the PC-pH diagram, but rather it's just asking us the concentration of Fe2+ at a given condition. So if we had a PC-pH diagram or PC-PE diagram at a given pH, we would just go and pick that PE value, so calculate PC for that given PE. But now here, we don't have that, so we just need to do the calculation as we always do to construct the PC-PE diagram. So let's focus on the reactions first. This looks like a standard redox reaction, so the equilibrium expression is this E0. This is a complexation reaction, but just be careful. This is Fe2+, not Fe3+. So basically the result of the redox reaction, the result of oxidation of Fe3+ is complexing with ammonia. And ammonia is also a part of acid-base reaction, and we also have a precipitation. So as you see, and as I mentioned, the very first useful approach would be basically to write down all the reaction diagram. So Fe3+ is in complex with is in redox equilibrium with Fe2+, so that's reaction 1, then E0. Then the reaction 2 is complexation of Fe2+. Again, I'm highlighting this to show this is not Fe3+, so Fe2+ is in equilibrium with Fe2+, so this would give us Fe1NH3 and 2+, this would be beta 1. The third reaction is talking about possibility of precipitation of Fe3 plus now with OH to form FeOH3 solid, KSP. And then we see that this ammonia is a part of acid-base reaction. Let me just write it in the bottom section, or this is good because it's just one. This is a part of an acid-base reaction. We need NH4 plus with Ka. So basically we have just a complexation, one complexation, and one redox, one acid base, and one precipitate. So as normal, as usual, we just continue with basically the equilibrium expressions. So this is something that we do for basically all the equations. So here is no exception. So let's start with iron. So the first useful expression would be basically the equilibriums. So let's drive the K values. So the first one is basically, this is equilibrium. So the first one is basically E0. It's written in the standard way, so this would be Fe2 plus, and then Fe3 plus times the concentration of electron, or let's just write it in the standard way. The electron. So let's just construct everything based on Fe3 plus. So then Fe3 plus would be basically Fe2 plus, or yeah, so if you want to do around Fe2 plus, so Fe3 plus, it has to be Fe2 plus here, because we want to convert everything to Fe3 plus. So Fe3 plus times E0 divided by the activity of electron. So yeah, this would be our first relationship. So the second one, based on the second reaction, is basically a beta value. So beta 1, it's just one beta, so we used basically beta 1, is FeOH, sorry, this is just the ammonia. So FeNH3, 2 plus, Fe2 plus, then ammonia. Therefore, we get Fe2 plus equal to Fe ammonia 2 plus divided by beta 1 ammonia. But we need to basically convert everything to have something on the right side as Fe3 plus. So what we do is basically use equation 1, insert it here, to convert the concentration to relate the concentration of the complex to eventually Fe3 plus. So 1 and 2, we have Fe ammonia 2 plus would be equal to beta 1 E0 E minus And yeah, that would be times the concentration of ammonia. Yeah, beta 1 ammonia and all times the concentration of Fe3 plus. So now we have the concentration of this complex related to Fe3 plus, and this is the term, the conversion term between these two. So let's call this equation 3. The fourth reaction is basically the precipitation reaction. We're going to use it later, but let's actually focus on the mass balance now. Reaction 4 is also something related to ammonia that later we can basically calculate the concentration of ammonia using that value and the total concentration of ammonia that is given. So now let's focus on the mass balance. So in terms of the mass balance, so we have two mass balances. One is for iron and the other one is for ammonia, basically. So for ammonia first, which is easier, let's take care of it. So we have this total ammonia, which is equal to the concentration of ammonia plus ammonium. And we know how ammonia and ammonium are related. So basically, let's just go back here. Have that equation also here, Ka1, or just Ka, would be basically NH3 times proton divided by the concentration of ammonia. So this equation 4 would basically can help us to directly find the concentration for ammonia, which later we need to use it in the equation for mass balance of iron. So NH3 would be basically the total ammonia divided by 1 plus the concentration of proton divided by Ka. So now let's do also the mass balance for iron. So the total dissolved iron would be basically iron 2 plus, or it's 3 plus, iron 2 plus, plus the complex with ammonia. Yeah, that's the only species of dissolved iron we have. So basically, we have either this, or this guy. This, we're still not working. This is basically what takes iron out of the solution. So we have this equation of equation 1 and equation 3 to basically replace the concentration of either complex or Fe2 plus as a function of Fe3 plus, so make it simplify. So let's replace them based on equation, what was the number? Equation 1 and 3. Yeah, 1 and 3. 1 and 3. Then the total Fe would be Fe3 plus Fe3 plus times E0 divided by the activity of electron plus that term that we drove. So now we have all in the form of Fe3 plus and then the total, and the rest is either constant or something that is condition dependent. So now, because we're also dealing with possible precipitation, we have to actually consider actually precipitation. So what we do, the strategy was defining two scenarios. So for no precipitation, this NP scenario, we basically can use equation 6. So the concentration of Fe3 plus would be total Fe, something that is given, divided by 1 plus E0 divided by the activity of electron plus beta 1 E0 divided by the activity of electron times the concentration of ammonia. So that's it when there is no precipitation. So basically this is the concentration of Fe3 plus NP. So with precipitation, we know that we're limited by the KSP, or by the maximum of Fe3 plus, what is basically precipitating, which is KSP divided by the ligand to the power of N. In this case, this would be basically the ligand is hydroxide to the power of 3. So if we look back to the reaction, this reaction, the K value for this reaction represent Fe3 plus times OH to the power of 3. So Fe3 plus concentration would be KSP divided by OH to the power of 3. So now that we have basically the values for PE and pH, so PE is basically 3, or the activity of electron is 10 to the minus 3, and pH is basically 5, so the concentration of proton is 10 to the minus 5, and the concentration of hydroxide is 10 to the minus 9. Then we basically calculate the concentration of Fe3 plus max, Fe3 plus no precipitation. As always, we pick the minimum because basically there is a limit of having Fe3 plus in the solution for this given condition, and that limit is basically the KSP value. So as you see, when we want to calculate this guy, we need the pH, which basically is given here. If we want to calculate this guy, we need basically the activity of electron, which is given here. And also we need to know what's the concentration of ammonia at that particular pH. And basically based on reaction expression number 5, we can calculate the concentration of ammonia at a given pH. This is basically constant and given. And this is basically constant at 10 to the minus 9.25. So the pipeline would be at pH. We calculate NH3. Then we come here at that pH and PE. We calculate Fe, no precipitation. Then at that pH, we calculate the Fe3 plus maximum. We compare these two, pick the minimum. And then because the question is asking about Fe2 plus, then when we calculate the Fe3 plus, then we use equation number 1 to calculate basically Fe2 plus. So let's do that. So at this given condition, we can do the calculation for the concentration of Fe3 plus for a no precipitation scenario, which would be almost 10 to the minus 6 molar. And then we can do the same calculation for Fe3 plus max using the precipitation scenario, and then that would be 10 to the minus 11.8. And no surprise, because of the solubility constant, Ksp was so low that we're expecting a lot of precipitation. So a small concentration of Fe3 plus in the solution. So the minimum value between the two, then it would be the concentration of Fe3 plus, the actual concentration in the solution in this case would be equal to Fe3 plus max, or 10 to the minus 11.8. So this is the concentration of Fe3 plus, the actual concentration. Then getting into equation 1, we can actually calculate the concentration of Fe2 plus, and that would be almost 0. So what it means is that the concentration of Fe3 plus is so low. The concentration of Fe2 plus is also very low. And when we look at the diagram, this is so low, this is so low. So obviously not much of this to go towards this one. So the complex is also so low. So what is happening is basically most of the total Fe is going to be in the form of precipitate eventually, because of the very low solubility of iron hydroxide, considering the pH and PE, basically. So most of it will be in the form of precipitate leaving the system. And eventually Fe2 plus would be almost 0, and also the concentration of dissolved Fe3 plus would be also very, very low. And then this would be also molar, and this is basically molar. So that's question 2. Let's now move to the third question. So reduction of lead using copper. So we have a version of this question in the class, and that version was basically at the standard condition, and the question was pretty simple. Can copper at the standard condition, copper 1 plus, reduced iron 4 plus? So pretty simple. But now in the homework, what we had basically was whether this happens at non-standard condition. So that's what we are trying to answer here. So this is whether this is going to happen at the non-standard condition. So the information is pretty much given about the operational condition, which is, as I mentioned, non-standard. So the concentration of individual species involved in the reactions are given, and also the equilibrium expression for the redox reaction. So we're not at standard condition, but this doesn't change the fact that which reaction was oxidation and which reaction was the reduction. So as mentioned, copper plus is reducing lead. So that means copper is a part of the oxidation reaction. So for oxidation, we basically have this copper plus oxidizing to, we don't know what, but this is basically the hint, is to copper 2 plus. And then for the sake of charge balance, we have 1 electron. And this is the standard reaction, basically. It's in the form of oxidation, and also we're releasing 1 electron. So the PE0 can be used, and this is basically for the oxidation. And for non-standard condition, this would be PE0 of ox. Then we have this reduction. It seems we're dealing with Pb4 plus and also Pb2 plus. And when we look at the oxidation number, this is basically plus 2, this is plus 4. So this would, Pb2 is oxidized to Pb4. So Pb2 plus, because the oxidation is basically increasing the oxidation number. So Pb4 plus, it's balanced in the same in terms of all the elements, which is basically only lead here. But for the sake of charge neutrality, we need to add 2 electrons. We cannot use this value that is given here because this reaction is not written in the standard way. So we basically need to convert it to the standard oxidation in the form that we're releasing 1 electron. So half Pb2 plus going to produce half Pb4 plus plus electron. Now for this reaction, we can use PE0, which is for reduction, and PE for reduction at the non-standard condition. So basically the overall reaction for copper 1 plus to reduce Pb4 plus would be copper 1 plus. So basically oxidation reaction plus a reverse of the standard of the reduction reaction. So copper 1 plus plus half Pb4 plus going to copper 2 plus plus half of Pb2 plus. When we look at it, it's charge balanced. So 3 charge here, 3 charge here. And also copper plus is oxidizing Pb4 plus. So that's exactly what the question is asking. And since this reaction is a combination of 2 standard reactions, then we can use this PE0 of reaction or PE of reaction at non-standard condition. So if this reaction happens, that means copper plus can reduce Pb4 plus. So in order to understand whether that reaction happens, that means we have to answer this question, whether the reaction is spontaneous or not. And to do that, we should calculate the actual PE of reaction at non-standard condition. So basically for PE, we know for PE of reaction at non-standard condition is basically a deviation from the standard condition by log Q. And PE0 of a reaction, we showed in the class that this is basically PE0 of the oxidation minus PE0 of reduction. Or in this case, this would be basically based on the number that are given, 2.69 minus 28.64, which is equal to minus 25.95. And so combining these two, PE of reaction would be minus 25.95 plus, and now we need to look at the log of this reaction, the Q, the reaction quotient of this reaction. So this would be log of the concentration of copper 2 plus, Pb 2 plus to the power of half, copper plus, and then Pb4 plus to the power of half. You see if this was standard, the concentration would be 1 for all of them. So this term would be 0. So PE reduction would be basically PE of reaction would be PE0 of reaction. But now this is the deviation from the standard condition. And then we basically have all the concentration terms that we need to put it here in this equation. So after inserting all of them, the value would be minus 26.5. And we know this is basically smaller than 0. That means delta G of reaction is smaller than 0. So this is spontaneous. So, long story short, that means at this condition, copper plus can reduce Pb4 plus. So, and as I mentioned in the class, this is very useful information to know. So in environmental system, we can evaluate what kind of element can reduce or oxidize another kind of element at a given condition in terms of the concentration and sometimes the condition of the solution. For example, if a part of our overall reaction was H plus, for example, which was coming from either oxidation or reduction, then that means the pH of the solution also dictates the Q, the reaction quotient, which eventually dictates PE of reaction and whether the reactions are spontaneous or not. So let's move to the last problem on a PE-pH diagram. So this is a similar question we had in homework 4. So the last question of the homework, which we were asked to construct the PE-pH diagram. As I mentioned in the class, this is a great diagram that we can use basically for determining what species is dominant at a given PE and pH. So rather than just knowing the actual concentration of the species, that can be easily calculated using PCPE diagram. Here, this PE-pH diagram would just give us the information about what species is basically dominant, which for most of the case, this is enough to know more about the system. So, as I mentioned in the homework and also in the class, when it comes to a metal, there are tons of possibilities, tons of different ligands, tons of different precipitation. So it's the best idea is to stick with what is given and just drive our equations or our lines in PE-pH diagram based on only the information that is given. No more, no less. So here we are given 3 species of iron. So iron 2+, 3+, and iron hydroxide. And it seems, based on the information that is given, we're expecting 3 redox reaction and 2 complexation reaction, because this beta. So that means 5 relationship between the species. And that means 5 lines we're expecting in our PE-pH diagram. So let's focus first on see what kind of redox reaction we expect and what kind of complexation reaction we expect. The best way is to always start with the species. Here we have Fe2+, Fe3+, and Fe hydroxide. And now let's look at the oxidation number. This is basically +2, +3, and this is also +2. Oh wait, we have one more species, and that's FeOH3, and that's +3. So it seems, as I mentioned in the class, when the oxidation number is changing, that means we have a redox reaction. And if you look here, those redox reaction, the information is given. But it looks like for some of the redox reaction, specifically between these two, which we expect a redox reaction to happen based on the oxidation number, we don't have that information here. So it seems it's not possible to jump from Fe3+ to FeOH2. So if we look here, that information is not given. So that's what I'm saying. Just stick to the information that is given. This would be a good way to figure out what you expect in terms of the redox reaction. So you expect the redox reaction between these two, and then you look here, and then you see that value is given. So that's how you proceed with that particular line. So here, the best way is to always start with the easiest. So basically the easiest is Fe2+ and Fe3+. So reactions. The very first one, which represent the first line, would be Fe2+ going to Fe3+ plus electron. This is a standard reaction. So basically E0 would be Fe3+ times E- divided by Fe2+. So let's just do minus log. This would be PE0 minus log of Fe3 plus over Fe2 plus. I just just decouple this electron term, so it would be minus log of the activity of the concentration of electron, which would be basically Pe. And then because these lines represent the equilibrium or represent the same concentration of these two, so this would be 1. So this whole expression would be 0. So then the first line, basically Pe is equal to Pe0 for Fe2 plus Fe3 plus, which is basically 13.03. So that's the first line. And as I mentioned in the class, for a simple redox reaction, which is in this case a simple redox reaction, no proton involved, so that would be just basically Pe is not a function of pH, it's just a constant number, and that's just a horizontal line. So now let's focus on the second line. Based on the information that is given here, let's work on this two, Fe2 plus and FeOH3. So Fe2 plus and FeOH3, as we look at the oxidation number, we expect a redox reaction. So it seems Fe2 plus is oxidized to FeOH3 because the oxidation number increased. So let's write it down. Fe2 plus is oxidized to FeOH3. We just need to balance it now. So this would be require 3 water to balance oxygen. Then it comes to hydrogen. This needs 3 hydrogen in the form of H plus 1 electron. And now this is basically a standard reaction written in the standard way. So we basically can use this E0, which would be FeOH3 times proton to the power of 3 times electron divided by Fe2 plus. I'm just making it simplified by not considering these 2 anymore, just because it would be always the same. That terms goes away. So this would be Pe0 is equal to 3 pH plus Pe, or Pe would be Pe0 in this case is 28 minus 3 pH. So that's the second line. Now let's see if we can draw it. The third line, which would be another redox, this time between FeOH2 and OH3, as we expect. The oxidation number changed from +2 to +3. So basically this is oxidized to this term, to this species. So we would have FeOH2 oxidized to FeOH3. So it needs 1 H2O, and this needs 1 proton and 1 electron. It is already standard, so eventually this would be Pe0, which is 7.5, minus pH. That's another line which represents these 2 pairs. Okay. So let's now focus. So we're done with the 3 redox reactions. So now let's focus on the 2 complexation reactions. So for the very first complexation reaction, so line number 4, we basically have this Fe2 plus 2 hydroxide is going to Fe hydroxide 2. So this is represented by beta 2 of Fe2 plus is equal to Fe OH2 divided by Fe2 plus hydroxide to the power of 2. Again, I'm ignoring that FeOH, Fe2 plus part. So let's do minus log. You can also log, it doesn't really matter. Then we get minus log of beta 2 Fe2 plus is equal to 2 log of hydroxide. Yeah, because that minus log, yeah, that would be log. So this means minus log of beta 2 Fe2 plus would be 2 log of Kw divided by, let's just, yeah, Kw divided by H plus, or we can expand it, 2 log of Kw minus log of H plus, or 2 log of Kw plus 2 pH. So if we insert the numbers, so we basically have minus log of beta, so minus 7.51 is equal to minus 28, because log of Kw is minus 14, so minus point, this would be 2 pH. Then we get pH equal to 10.25, the vertical line as we expect. And if we basically do the same thing for the last reaction, so the complexation of Fe3 plus 3 hydroxide, we get the same sort of vertical line, but this time that vertical line would be at pH of 5. The same procedure, the same exact procedure we take for calculating the line, basically beta, then Kw, then KOH. So now we have these 5 lines, 2 vertical lines, and 1 horizontal line, and 2 lines that are both, they have both components of PE and pH. So if we go to Excel, basically put all of these lines together, this would be the actual line without erasing any part. So just keep in mind, without erasing any part. So the first line, the 2 horizontal line, as I mentioned, 2 vertical line, and 1 vertical line and 2 lines that have the components of PE and pH. This is basically water, for water oxidation and water reduction. So this is water oxidation, which we actually showed in the class, the formula 20.8 minus pH, and this was basically the minus pH, which was water reduction. So let's go step by step. We know all the lines that are outside of this window will be limited by water. So basically this part, this part, this part, this part are not playing a role here. So now let's just focus on the individual. So this line is basically dividing this section and this section into Fe3 plus, this one, and FeOH3. So that means all the lines here that they don't have equilibrium with Fe3 plus would disappear. So let's go one by one on the lines. So this line represents Fe3 plus and Fe2 plus, right? So after this point, there's no more Fe3 plus or 2 plus, because this is based on this line dominated by FeOH3. So basically this part of this gray line would disappear. So only this part of the gray line is acceptable. So we took care of the gray line. Now let's take care of for example, the red line. The red line. So the red line represents FeOH2 and FeOH3. So as I mentioned, this region is for FeOH3. So far, this part of the line would go away. So that part of the line is not acceptable based on this criteria. But when we look at the green line, we see that the green line has Fe2 plus region and FeOH2. So basically this line, which has nothing to do with Fe2 plus, cannot be in the region of Fe2 plus. So this part of the red line also goes away. So the only part that stays is basically this part. And this would be this part so far. Yeah. Now let's focus on the yellow line. The yellow line is between Fe2 plus and FeOH3. So first of all, based on this line, we know this side is FeOH3. So this cannot be a part of it because this is the Fe3 plus region based on this line. So that part of the line is gone. And now let's focus on this part. This part based on this green line is the territory of FeOH2. But this is related to FeOH3, has nothing to do with FeOH2. So this part is also gone. So the only part that is left, which makes sense thermodynamically, is this part. Yeah, so that's another part. So now we took care of the 3 of the lines, 2 more left. So now let's focus on this guy itself. So this line basically divides the graph into 2 sections, this section and this section. This line basically represents Fe2 plus, Fe3 plus. The more reduced species, which is Fe2 plus, stays in this region, as we talked in the class. So this is basically the Fe3 region, Fe3 plus region. And so this is Fe3, this is Fe2. So now let's look at this line. This line contains Fe3 plus. So this part of the line is the only side that makes sense. This is Fe3 plus, this is Fe2 plus. So this part which is in the Fe2 plus side based on this gray graph cannot be a part of this gray line, which has nothing to do with Fe2 plus. And we know we're limited by water, so basically we go up to here. It's like the, yeah, not that. So the only part that is left is basically the green line to trim it. So we don't care about the part that is outside of the window. We just need to do these 2 parts. So these 2 parts, based on the red line, it seems we are dealing with FeOH2 and FeOH3. The more reduced species stayed in the bottom. The more reduced species is basically, when we look at the reaction, this was the last reaction. So the reduced, if we have more electron, it would be FeOH2. So that's the reduced species. So in the bottom, we have more of Fe2 plus. And on the top, Fe3 plus. And then this line has nothing to do with Fe3 plus. So this top part doesn't make sense. So the only part that is left It's basically this part. So now we trim the line, and what we get is the region for, so this is basically O2H2 limited by water. So this is the region for FeOH3, FeOH2, Fe2 plus, and this is Fe3 plus. Or to make it to have like a clean, more clean graph. So this basically is the clean version of this graph. Nothing new, it's just a little bit more organized. Yeah. So as you see, Fe3 plus, Fe2 plus, we just removed the line, the part of the line that wasn't thermodynamically feasible. So just a little bit practice on trimming the line. That's probably the trickiest part. But the rest is basically the simple algebra of constructing the line. The whole idea of constructing a line is to have a equation that is related to PE and pH. Sometimes it's only related to PE, sometimes it's only related to pH, and sometimes it's just a blend of them. Then you put all of them in the graph. And the next part would be making sense of the thermodynamic in order to cut the part of the line that is not, that doesn't make sense. This question, we were asked to consider also water, but sometimes for the sake of simplicity, the question is asking you not to consider water. So basically, you extend this line up to here or extend this line up to here. This is basically all about the chapter 3 and chapter 4. We talked about metals, either their complexation or their reduction and oxidation or redox chemistry of them. And sometimes either the reduced or oxidized species can undergo complexation reaction or precipitation reaction. But if we put everything into this reaction diagram, then it would be very easy to discuss the equilibrium expression, and then based on that, if it's needed to calculate a certain concentration at a given condition, which was, if I'm not mistaken, problem 2, then we can easily calculate the species concentration. Or a graph is needed. That means we need to come up with the equations of the line, for example, the problem number 4, and we can use that to construct the graph. But again, it would be very easy to have that reaction diagram. And sometimes, especially for PE-pH diagram, don't confuse yourself. Just go with the reaction that their constants are given. Because we know metal complexation, metal redox can be very involved. So we don't have information about all of them, so just stick to what is given. Okay, that's about it, and that's about this whole course. Chapter 1, we talked about to introduce some fundamentals on environmental chemistry. The second chapter, we talked about acid base and all the related phenomena. Chapter 3, metal chemistry. And then chapter 4, redox chemistry. But we saw that all of these chapters are heavily connected together. So basically, it's all about the environmental system that we can, at the end of this course, model and talk about a speciation at equilibrium, or if it's not at equilibrium, predict the direction of the reaction to get to the equilibrium. Thank you so much, and have a good one.